Hi, everyone. I figured I'm going to get a fair number of questions, and I already have on 8.2, number 20. So I'm going to go ahead and preemptively come in here and kind of talk through some specifics. I've told a number of you some of this stuff already, but I'm going to go into a little bit more detail just so that hopefully it makes a little bit more sense. Okay, so the setup is the following, and I don't think it really matters whether you imagine the cards. So you have N cards, and they're numbered 1 through N, and they're stacked in order. And I don't really think it matters all that much whether you think of them with 1 on top and N on the bottom, or vice versa. But just for the sake of simplicity, let's just think of the top card being 1, the second card being 2, the third card 3, all the way down to N, the card that's on the card that's on the bottom on the table. Okay, so overall you have something like this. It's like 1, 2, 3, 4, dot, dot, dot. Here's my stack of cards, N, like that. Okay, so that's the stack of cards like that. Okay, and what's going on here is you're picking random numbers. So you choose random numbers from the set 1, 2, dot, 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 N, without replacement. Okay, without replacement. So that means, once I pick a number, I kind of throw that one out. I throw that one out. Okay, so, and you keep doing this until you completely eradicate the entire pile, which means you keep going until you draw the number in, because the minute you draw the number in, you're going to completely eradicate the pile of cards. It's going to be gone. Okay, so for instance, suppose I drew, like 3, and then after that I drew 2, and then I drew 6, and then I drew N. Okay, all right. So what would that look like? Well, it would look something like this. It would be basically, 1, 2, 3, 4, 5, 6, 7, N, like that. So the first card, the first number you drew was 3. So you would remove card number 1, 2, and 3. And so the top card would be 4 at that moment. And then the second number you draw is 2. So right, the first number we drew was 3. The second number we draw is 2. Well, that one doesn't really end up doing anything to our pile of cards because 2 is already gone. Okay, we've already kind of gone down and removed 2, so that's gone. And then we go to 6, so that means we go 4, 5, 6, so that one's gone. And then we drew in last, which means we then just go, all right, and the whole thing is eradicated and we stop the process. And because we're drawing these random numbers without replacement, basically a drawing sequence is kind of an incomplete permutation. Like it doesn't have all the numbers in it. It's still a permutation, okay? It's a permutation of some of the elements with N at the end, with the number N at the end, because the minute you draw in, the process stops, okay? So a drawing sequence, let me kind of write this down. A drawing sequence corresponds to a permutation with N at the end. Okay, a permutation, but the thing is, the permutation doesn't have to, so we have to be careful about what we mean by a permutation. The permutation itself might have, I just want to make sure I'm not losing you on the board here. Let me just make sure this thing is not, okay. Okay, so permutation with N at the end. So the permutation itself might have not all the elements in it. So this permutation could be in any length. could be of any length greater than or equal to 1 and less than or equal to n. So the permutation could be any length equal to or greater than 1 or less than or equal to n. Even the, let me just separate this out. Even like the permutation in itself would be one drawing sequence, because if I drew in immediately, the process would just immediately stop, okay, and we'd be done. Okay? So there we go. So let's kind of think about that. So here's the question. Here's our first question. Okay. How many drawing sequences? So what's the number of drawing sequences? Number of drawing sequences equals number of drawing sequences equals what? Okay, so what is it? Okay, what is it? Okay, so remember, a drawing sequence corresponds to a permutation that ends in n and then just has other numbers before it, but no numbers get repeated. Okay, once we draw a number, that number is gone. Okay, well, so what about length 1? Length 1 drawing sequences. Okay, well, that's just n. Okay, that's just the number n. Okay, you would have to just do that one. So there's exactly 1. Okay, so there's 1 of these. What about length 2? Okay, length 2, well, that means we have something like this, blank n, like that, right? So blank n, okay, so there's going to be a total of n minus 1 things that would work in this particular case. Okay, okay, what about length 3 drawing sequences? Well, okay, so a length 3 drawing sequence would be like, okay, something, something, n, like that. Okay, well, how many ways are there to fill in? How many ways are there to fill in these two things right here? How many ways are there to fill those in? Well, from the n minus 1 other numbers, I would have to choose 2 things. And then I would have to order them in 2 ways. Another way to think about that is I basically have to put 2 numbers in those positions, because order matters here. I have to put 2 numbers in those positions from n minus 1. So it's really p n minus 1, 2. And actually, n minus 1 itself was p n minus 1, 1. Okay, so that's interesting. And I can even think of 1 as being p n minus 1, 0. Okay, if you want to think about that, because remember, what's the formula for p in r? Well, it was n factorial over n minus r factorial. Okay, so p n minus 1, 0, well, that would just be n minus 1 factorial over n minus 1 minus 0, which is just n minus 1 factorial, and you would get 1. Okay, so that's what the formula would be. Okay, and I think you see the pattern now. What about length 4 drawing sequences? Okay, what about length 4 drawing sequences? Well, that would be 1, 2, 3 options before the n. Okay, and of course, the number of those is going to be p n minus 1, n minus 1, 3. Okay, because that's the number of ways to fill in these first 3 positions. Yeah. Okay. Okay. That's curious. So what's the size of the universe here? The size of the universe is equal to, okay, well, it's going to be the sum, I going from 0, okay, the 0 case happened for the length 1 drawing sequences, the 1 case happened for the length 2, etc. It's going to be p n minus 1 I. Okay, I going from 0 all the way up to what? What's the most this thing could be? Well, I could have a length n drawing sequence. N would just have to be at the end, and I would just have to put all n minus 1 numbers before n, okay? And that would be n minus 1 put in, which is really just n minus 1 factorial. So I could go all the way up to n minus 1. Okay, so that's really surprisingly, counting the size of the universe is kind of the key to this problem. Okay, so once you understand it, everything else starts to kind of fall into place. Okay, and let's see why. All right, so so let me just rewrite this thing, this formula. The size of the universe, which is the size of all drawing sequences, equals sum I going from 0 to n minus 1, p n minus 1 okay, like that, okay? Bearing in mind that I equal to 0 corresponds to length 1 drawing sequences. I is basically always 1 less than the length of the drawing sequence because they always end in the number n, okay? And another thing I wanted to point out was the following. I think I've said this a few times, but e to the x is equal to 1 plus x squared over 2 factorial plus etc., right? We know that. Okay, the famous power series for the exponential, or Maclaurin series more precisely. So e to the x, this is sum. Let me say k going from 0 to infinity, x to the k over k factorial. And so, so interestingly, for any given x, I mean, this power series converges very quickly to the exponential. You don't have to take a whole lot of terms to get a pretty good approximation for e to the x, okay? So, so e to the x is approximately just add up a decent number of these terms, okay? So what about the number e? Okay, well, e is equal to, or is roughly equal to the sum k going from 0 to m. And now I've actually plugged in x equal to 1, right? I've plugged in x equal to 1, so it's just going to be 1 over k factorial. Okay. All right, so why is this relevant? Why is this relevant? So this is for m, m large, okay? M relatively large, I would have a pretty good, and it would keep getting better the larger m got. But it's really not all that far off, even if m is, not all that large, like 10 or something, you'll have a really good approximation for e. Why is that relevant? Well, it's relevant because when you think about it for a second, this sum up here is going to be equal to something. The size of the universe is going to be equal to something that involves something that looks like the exponential. And we'll see why here in just a sec. So watch this. Okay, so what about the size of the universe? Okay, well, once again, it's equal to the sum, I going from 0 to n minus 1, p n minus 1 okay, which is equal to sum I going from 0 to n minus 1. This is going to be n minus 1 factorial over n minus 1 minus I factorial. Okay, and check this out. This guy I can pull out. And this n minus 1 minus I, that's just, if you think about it for a second, this is going to be n minus 1 factorial. Okay, let's just open a parentheses. If I plug in 0, I get 1 over n minus 1 factorial. If I plug in 2, I get, or if I plug in 1, I get n minus 1 over n minus 2 factorial. All the way up to plugging in n minus 1, I get 1 over 0 factorial, which is, okay, so this is going to be 1 plus 1 over 1 factorial plus 1 over 2 factorial plus blah, blah, blah. Where does this end? Where is this going to end? Well, at 1 over n minus 1 factorial. Okay. And what's this approximately? Well, that's approximately E. Right? So the size of the universe is approximately n minus 1 factorial E. And that really is the key to everything. The size of the universe is approximately by this, is approximately given by that. Okay. So, all right, so let's move on to the next little step here. So now I want to know, they said, what's the probability that at some moment I end up with the card on top actually being drawn? Okay, so let's name those sets. Okay, so like, you know, A1 is going to be sequences, drawing sequences with one on top and chosen while on top. Okay, so A1 is sequences where one is on top and it gets chosen while it's on top. Well, that just means that immediately you'd better choose one at the very beginning. Okay, and so A2 is equal to sequences with 2 on top and chosen, okay, etc. You know, all the way down to AN is sequences with N on top and chosen while it's on top. So, and by the way, on top at some point, right? At some point. And chosen while on top, okay? One thing that you have to keep in mind is that in order for something to be chosen while it's on top, it needs to have the card above it selected at some point. So for instance, like if the card 3, the card that's 3 from the top is going to get selected, that means that the card number 2 has to be selected before it, okay? Now, so those A's are, you know, nicely defined. So what do we want? We want the probability. They said that they wanted us to compute the probability that something happens. We want the probability that A1 happens, or A2 happens, or A3, or ... right, or AN, right? So that's the probability of the union of these things. Okay, so let me just say that we want the probability of A1 or A2 or ... or, you know, AN. Okay, so the principle of inclusion-exclusion works just as well for this as it did for counting, right? I mean, essentially, this probability you just divide by the size of the universe anyways. So essentially what you end up with is this is going to be the sum I going from 1 to n probability of AI, okay, minus the sum 1 equal to or less than I less than j equal to or less than n, the probability of AI and AJ, okay, plus, and you know what's going to happen, right? What's the last thing going to be? Well, it's going to be -1. Okay, let's see. This thing is kind of off. You know, so if I have pairs, it comes with a minus sign. So it's actually, the parity is the opposite of the number of sets you're intersecting. So we'll say -1 to the n minus 1 times the probability that all of them happen. Okay, that would be a very interesting, look, I mean, just think about it. A1 and A2 and et cetera and AN, what in the world would have happened for that to occur? Well, that means A1 was on top and it was chosen, right? So what does that mean the drawing sequence had to be? Well, that means you had to choose 1 while it was on top, and that uncovered 2, and then you had to select 2 while it was on top, et cetera. And actually there's exactly one permutation that's going to have that's going to have that occurring, and it's the permutation where it's just 1, 2, 3 all the way down to n. Okay, that's that last one's pretty easy to compute. But actually, we're going to spend all of our time just thinking about this, and we're going to notice something amazing that happens, and here it is. So let's think about this. What about the probability of a n? Okay, so what in the world is going on with that? Okay, what in the world is going on with the probability of an? What happened in order for an to occur? Well, what that means, okay, so for an to occur, what that means is that blah, 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 we were doing our drawing sequence, and at some point we had to uncover the card with n on it, the bottom card. We had to uncover the bottom card so that it's on top, and then we will select it at some point. Okay, it doesn't even matter what happens. Once we've uncovered it, we know that no matter what numbers I'm drawing out of that hat and setting aside, that eventually I'm going to draw in, and it's going to be on top when we do that, right? So this thing has to look like this. It has to be like, oops, let me get rid of that. So this thing has to look like this. It has to, at some point we had better draw n-1 so as to uncover that bottom card. And then we do some other stuff, and then we end with n, right? A sequence that looks like that is guaranteed, right? Is guaranteed to have us uncovering n, right? This is exactly what has to happen. If n-1 wasn't there, if n-1 wasn't there, then we wouldn't uncover the bottom card so as to select it while it was on top. Okay, so how many of these are there, right? So how many of these? So what is the number of these? What's the number of these sequences? Well, what we're going to have to do is figure out, I mean, even like just n-1 by itself with n would be legitimate, okay? So from the n-2 other numbers, we need to select some number of things to put in here, okay? So for instance, you know, we could have a length 2 sequence that looks like this, okay? But we could also have a length 3 sequence, okay? You know, a length 3 sequence with n-1 somewhere. Okay, so it could be n-1 blank n or blank n-1 n, okay, etc. Okay. Now, here's the thing. What we really realize is it's like, okay, what I need to do is choose some number of integers other than n-1 to put together with n-1, and then we just arrange those in front of n somehow, okay? I might even choose 0 of them, okay? Might even choose 0 of them, okay? So let's kind of look at that, okay? So length 2, so remember we're doing this, n-1, blah, n, okay? So how many are there? So what about length 2? Length 2, okay? Well, that means that from the other n-2 things, I choose 0, and then I basically arrange everything in front of n, but that's kind of silly. There's only one thing to arrange. There's just n-1 itself. So I'm going to multiply this by 1 factorial. Okay, what about length 3? Well, from the n-2 other numbers, I need to choose one, n-2 other numbers. I need to choose one to put with n-1, and then I'm going to take that number and I'm going to arrange it with n-1 in 2 ways, or 2 factorial ways. Okay, length 4. length 4 things. Okay, if it's length 4, I need to choose 2 more things. Okay, 2 things, and then I need to arrange the 3 total things, the 2 I just chose, together with n minus 1 in 3 factorial ways in front of n. Okay, etc. Okay, what's the last one going to be? So the length n, okay, length n permutation. That means I'm going to go n minus 2, choose n minus 2. Okay, because I have to take everything to get a length n thing. Okay, so, and I'm going to multiply that by n minus 3 factorial. Okay, all right. So what does that tell us the size of AN is? Okay, so let's look at that. What's the size of AN going to be? Size of AN is going to be equal to what? Well, it's going to be the sum of all those things. So it's the sum, I going from 0 to, what was it, n minus 2. And what was I doing? Remember, it was n minus 2, choose I. Okay, and then what were we multiplying this thing by? Well, it was I plus 1 factorial. I plus 1 factorial. Okay, so that's interesting. Well, I think that this is going to be similar to what we had before. Okay, there's a little bit of nice cancellation that's going to happen here. So first of all, this thing is n minus 2 factorial over I factorial, or let me write it this way. N minus 2 minus I factorial times I factorial. And this I factorial basically cancels the factorial off of that. And I can take the n minus 2 out in front of the of that thing over there. Okay, so let's think about that. Let's think about that. So what's going to happen? So this thing is going to be n minus 2 factorial. And basically the I factorial left that I plus 1 behind. So it's going to be sum I going from 0 to n minus 2. And what do I have here? Well, I have I plus 1 over n minus 2 minus I, n minus 2 minus I factorial. Yeah. Okay. And let's put J, just to simplify things. Oh man, let me erase this. Okay. So let's put J equal to n minus 2 minus I. Okay. Let's put J equal to n minus 2 minus I, just so that denominator is just straight up J. So that means, what is J going to run between? Well, J will run between the same thing that I ran between 0 and n minus 2. And what's I plus 1 going to be equal to? Well, I plus 1 is going to be equal to n minus, so like if you add I plus 1 to both sides, I plus 1 to both sides of this equation, you get I plus 1 on this side. Over on that side is going to be n minus 1. So it's like n minus 1 minus J. Okay. So what does this thing turn into? Okay. Well, it's going to be n minus 1 minus J over J factorial. N minus 1 minus J over J factorial in the summand. Okay, so it's going to be size of AN is equal to, oops, I already forgot. So it's n minus 2 factorial times the sum, J going from 0 to n minus 2 of what? Of n minus 1 minus j over j factorial. Okay, minus j over j factorial. There we go. Okay, and you might say to yourself, what on earth is that? Well, it's not too bad actually. So let's see. This is like n minus 2 factorial. Let's write this. I'm going to split it up into two sums, one that has this and one that has that. Okay. And of course, j is, when j is 0, okay, so let me just kind of multiply this. So the n minus 1, if you think about that for a second, I can pull that out in front of the sum. So this is going to be n minus 1 times the sum, j going from 0 to n minus 2, 1 over j factorial. Okay. And then actually the second sum doesn't start with 0, because the 0 term disappears because there's a j in the numerator, right? So it's going to be minus the sum. Let me write it this way. So it's the sum j going from 1 to n minus 2. The 0 term goes away, of j over j factorial. But j over j factorial, that's just 1 over j minus 1 factorial. Okay, which, I mean, if you think about it, that's just the shifted sum of reciprocals of factorials, right? J equal to 1 gets 1 over 0 factorial, j equal to 1 over 1 factorial, etc. Okay, so all of this is in parentheses right here. This guy right here, once again, that's approximately E. And what about this guy right here? Well, that's approximately E also. So the size of AN is just n minus 2 factorial. Okay, and then I have n minus 1 times E, right? This is approximate. N minus 1 times E minus another E. Okay, so n minus 1 times E minus E is basically n minus 2 times E. Just think about it for a second. Okay. And that's amazing, because now we know how to compute the probability of this thing. Okay, the probability, and we spent a fair amount of time computing this. And you might say, oh my goodness, how are we going to do the whole problem? Well, we're going to be able to do it because we realized something pretty quick here. Okay, so AN was n minus 2 factorial times n minus 2 E. Okay, and what was the bottom? That was back here a little ways. We computed roughly the size of the universe. That was back here. n minus 1 factorial times E. Yeah. Okay, so n minus 1 factorial. So here we go. So this is n minus 1 factorial times E. And lo and behold, what happens? The E's cancel. Okay. Everything cancels here. This n minus 2 factorial, all of that is going to cancel. And this, the only thing that's going to be left is the n minus 1. So this thing is going to be n minus 2 over n minus 1, which, by the way, is what? It's like this is n minus 2 is n minus 1 minus 1. So this is the same as 1 minus 1 over n minus 1. You say, what? So the probability of just AN is approximately 1 minus 1 over n minus 1. Okay? So just computing that, you already have seen that it's almost 100% likely that it's almost 100% likely that at some point you're going to draw the card in while it's on top. Okay, so with 100% probability, that's what's going to happen. Almost 100% probability, that's what's going to happen. So I just wanted you to have to kind of think through that a little bit. It's some nice combinatorics going on here, some nice estimation with the exponential thing. So overall, you see that the probability of this union, by the way, the probability of this union is clearly bigger than or equal to the probability of AN. Okay, AN happening implies that one of these other, in particular AN happened. And this thing is roughly 1 minus 1 over n minus 1. You could think about the other ones, but really that's kind of the key of everything that's happening. Okay, that's really the key of it, the key to everything. Okay, right there. And that's really all I cared about you doing. Okay. I think that's all I'm going to say about that for now. I just wanted to put that out there so that you guys had access to this and you could come over here and watch it. That's a pretty complete explanation of what's happening. If you want, you can go and look at some other ones. I don't know if you'll have time to do that, but it's a fun little exercise. There's some nice things going on, and I hope you agree with me. Thanks for watching.